Alright, hell yeah. So we're going to do double integrals today. This was a really good video to watch. And, I got like 9 minutes in. I'll finish it. But, heck yeah. This just kind of shows you the process. This is the Houston Math Prep. And really does a really good job of explaining. But there was a point in there where I'm just like, I didn't know how to set up the limits of integration. It seemed like kind of counterintuitive. So we're going to set up this problem and do it a couple different ways. So we have the square root. This is an equation, y is equal to the square root of x. We're going to go from 0 to 4. That's going to be our x bound. Now we have this little chunk, small little area dA. Now it does have little width, dx, and it does have little width this way, dy. Now this is kind of the plow method that I use, Might as well set this distance x over to that and set this distance y over to this. Now I think in this video they do it something different. And so I'm just going to go back to, the way that I would be able to do this if I got stranded on a desert, tropical, I don't know, you know what I mean? Like if you get stranded on an island and you wanted to do a double integral, I guess this is the way that I would have to do it. But hell yeah. And then this came up a lot in my engineering book where they just have this integral and dA. This video did a very good job of explaining, hey, you have a region here. This is kind of like they call it R. In a lot of engineering books, they just call it the area, the region of the area. So you have like a bean shape, and hey, there's your little dA, and then this is the integration over that region. But, I mean, if you're really going to do it, you might have to, come up with an equation for this line, an equation for this line. I don't know, you know what I mean? And just make sure they don't overlap. But so we're going to do this with the double integral, meaning slices. Alright, so the first one that we're going to do is, and we're going to have this little dx and dy. So let's say I wrote it like this. We have this little dx, and we have a distance x away. So this is what I did in the video. Made some mistakes, so we'll see if we can make less. I also know that this equation is if I square both sides. This equation is x is equal to y squared. So if I am going to take this little width dx, you know what I mean, and then move it from, in this direction, the x direction. Well, I can't start at, if I have it up there, I have to start like right there. And so that location is going to be y squared. And then I can go all the way over to x is equal to 4. So that's kind of what we do there. And then so this is that integral. Then once we get that, once we sum that all up, we get that little area. And then, heck yeah, you know what I mean? This little area, this is our new dA. And it has a height, or it has a width dy, and I guess this first integral actually gives that height. That height is this equation that we chisel out. So that is kind of fascinating. And yeah, that's interesting. But what we're going to do is we're going to integrate that from 0 all the way up to this top integral, which if we throw in y is equal to the square root of 4, we get 2. So in the y direction, we're going to go from 0 to 2. That value is 2 right there. So we're going to go 0 to 2. All right, hell yeah. So let's do it. So when we integrate this, we're going to get x, and we're going to evaluate from 4, y squared to 4. And then we're going to have still dy 0 to 2. That's going to be integral 0 to 2. This is going to be 4 minus x squared. So we got 4 minus y squared dy. Cool, now we just do the second integral again. So we have, we're going to integrate this. We're going to have 4y minus 1/3 y cubed. Integrate from, our limits of integration are 0 to 2. So we're going to have 8 minus 4 cubed, I'm sorry, 2 cubed, and then 1/3. So we're going to have 8 minus 1/3 times 8. So we have 8 minus 8 1/3. multiply 3 top and bottom, we're going to have 24 thirds minus 8 thirds. And that's going to be 16 thirds, which is, 15 thirds is 5. So we're going to have 5 and a third. Hell yeah. So we got the answer there. Okay, so now what we're going to do is the opposite. We're going to do limits of integration, dy dx. Alright, booyah. So if I have this little chunk, little dy, and I want to integrate it from 0 to right there, you know what I mean? Well, it hits this equation, so that's going to be 0 to square root x. Alright, hell yeah. And then once I do get that little strip, then I'll take that little dx, and then I'll integrate, and then I'll, add up the slices from 0 to 4. Okay, so sweet. Alright, so this becomes y evaluated at square root x, 0 to square root x, dx, 0 to 4. And then so this is the integral 0 to 4 square root x dx. Hell yeah. Now we're going to integrate this, and we're going to get x. This is going to be x to the 1/2 plus 1 divided by 1/2 plus 1, evaluated from 0 to 4. Cool. And we're going to have 4 to the 3/2 divided by 3/2. Sweet. Now, if you see this is 4 cubed. You could do that, or you could take the square root of 4. So that's what this divided by 2. So let's do that. Square root of 4 is 2, and then we're going to cube it. And then this, because it's a fraction, we can invert it, invert that fraction. And so we're going to have 8. 2 times 8 divided by 3. That's 16 thirds. And hell yeah, we got the answer. I don't know, you know what I mean? So this wasn't a very good video. But this was my second time around. Now I'm going to go through this whole process. And we do make a lot of errors. But I don't know, you know what I mean? Are these videos worth it? I don't know how to do this as of 3 hours ago. I watched a little bit of a video and ran into a place where I'm just like, I don't know. Like the way that they did it, I don't think I could. It seemed like a memorization technique where I just didn't see the plow your way through it. Like I just wanted to plow my way through it, so that's what we did. Anyway, so now the rest of the video starts. If you want to see me make errors on this, I could probably make a third video of like, hey, can't I do this faster? Because that seemed like a hell of a lot of time even just to get to there. So anyway, well, thanks for joining me, and continue on if you want to continue on. Alright, hell yeah. So today I'm going to try to do some double integrals. And this was a great video. This is Houston Math Prep. I got about 9 minutes in, and I'm like, hey, I'm going to make my own video. And so this is Houston Math Prep, finding areas using double integrals. Now, one thing that came up in this video was how to set your limits. And it seemed like the video creator, I don't know, it just had a way of saying like, well, do this, then that. And I just couldn't see it. So what we're going to do is take that, and I think that happens a lot, especially in textbooks. You're like, I don't see how you got from point A to B, and it seemed like you just used like a trick in your head or something. And that may be intuitive to you, but I just don't see it. So that's what we're going to do. We're gonna tear this one apart. So the problem at hand was this equation, which is y equals to the square root of x. We can also write this as x to the 1/2. And we're going to find the area from x. So this is our x-axis. This is our y-axis. So positive x, positive y. We're going to find the area from x is 0 to 4. And when x is 4, we can throw that into our equation. Y is the square root of 4. That's going to be 2. All right, sweet. So we're gonna have this, and even right now, it's like something that I see. Why I'm learning this? Bring this back up. Get some more advertising for Houston Math Prep. Yeah, just a really good job. Just really clear, exceptional. I'm trying to be exceptional, but it'll be a long road to become exceptional. Alright, so I don't even know what I was talking about. Oh, yeah. So why we have to learn this is because some of the textbooks, they do something like this. You know what I mean? You have this symbol, integration of dA. And I didn't even realize that they do this. They put this A down here. And from this video, Houston Math Prep, outstanding. Right at the beginning, this video creator really goes into talking about how, hey, this is the region you're talking about. And so a lot of textbooks will be doing something like this. Be like, hey, you just got a blob of area, and you're like, it just makes it 10 times worse. But, you know, and then you got this little box you're calling dA, very, very small little area. Now, it's got dimensions. You know, if we this has got dx. So that's kind of what we're going to do, is see that this has dimension dx, dy. What was I saying? Yeah, so the integral for this area, to find all the area inside that little bean shape, would be integral dA, and then this little a down here. Now, I don't know if I just didn't pay attention in college, or it's just like, if you miss that part, they're not going to re-explain it. But yeah, that little thing is the region. And so this symbol, in and of itself, comes up a lot. It comes up in moment of area, because if you take this area and then just multiply it by a distance, area times distance is the first moment of area. And then you would use that first moment of area. You would take, like, hey, integral of dA times, you know, some sort of distance, and then divide it by that area. Hey, this is going to give you, and let's do a visual on that. So so we do have this little area, you know what I mean? And then it's a distance away from the x-axis. So what would that be? That would be a moment of that area. And so for the problems that I'm trying to do, like even finding the centroid based on the first moment of area. And what that means is the first moment of area, just like you have a moment of a force, is force times distance. Well, because this distance is to the first power, you're just taking that force and multiplying it by the distance. That's what gives you that first property. This is the first moment of a force. If you wanted to find the second moment of a force, it's not really a term that's used, but it would be F times d squared. But definitely second moment of mass is definitely used. That's a moment of inertia for dynamics problems. I'll do I dynamic, and that's going to be mass in kilograms times the distance squared away from, you know, some sort of point or an axis. So yeah, it's the second moment of mass. That's what that comes into play. But hell yeah, so these problems of finding the centroid of something are just way easier when you have, like, when you treat this this area as like a force. You know what I mean? If I had a force sticking out and I wanted to know, hey, like if each of these areas had like a force sticking out, and then one way that you could visualize that is change your coordinate system xy. Now here's z, and we're going to say this is the up and down. So z is up and down, and then we're going to take that bean shape, and we're going to say, like, hey, let's say it's a 1-inch thick chunk of steel. That's pretty wide and stuff. You know, it's got that dimension. This would be 1 inch. And so now what? And now like let's say you're a human being right here, and then you have a big old arm, and you need to hold, you know, this chunk of steel. It'd be really heavy. It'd almost be impossible to do if this was 1 inch. That'd be too much steel to hold with your arm. But you can see that if, you know what I mean, you brought that in, you know, and got that like right underneath your arm right there, hell yeah, that would be less. So yeah. And then I guess what I'm getting at is this is a hell of a lot of leverage on your arm. You know what I mean? It's like a moment of a force. You have a force and then a distance. You're like, holy Toledo. Now, if your objective is just to hold the thing up, it's still going to require a lot of force. But if you did it with no distance, it's going to be way easier than to put it out here at any sort of distance with your arm. Alright, hell yeah. And I'm having deja vu because I swear I've done this one before, and this is not like even close of what I even wanted to you know what I mean? The moment of area to find the centroid is more like, hey, I just want to balance this thing. So what I'm going to do is I'm going to come in here with a spindle, you know what I mean? Maybe like a spindle and a point. And there's going to be a point that I can actually just get this and maybe this is a little flat spot, you know, to help us out. If it was a point, it would be very impossible to balance. But hey, let's say that we just have a 1-inch flat little table, and it's this conical shape. And then we can place this table somewhere where the whole thing doesn't tip over. It's not going to, if we look at it, you know, kind of in this Y direction and this X direction, it's not going to, and then we would, if it tips over this way, it's tipping about this X-axis. You know what I mean? If there's too much weight over here, then it's going to just kind of rotate that way about the X-axis. If it's too much weight over here, it's going to rotate that way. Now we can look down the Y-axis. If it's too much weight over there, which it looks like there is, hey, that thing's just going to tip this way. You know, so we would want to shift this thing to where this point looks fairly in the center. Okay, so I guess what I was getting at is if you treat, and this is the same thing as like, hey, you have a little chunk of area here. Like, why does that area attribute to a moment? You know what I mean? What we say with area is like, hey, it has some sort of directional face. So we can say that every little chunk of area on this disk is pointed up. Cool. Where if you look at it as weight, you know what I mean? Hey, every little chunk of volume right here has a force down towards the center of the Earth. Okay? And I think that can be easier to see, is that every 1-inch chunk of steel that you can chisel out of this thing has a force of about 1/3 pound, you know, 0.929 pounds. So now you can kind of visualize that. And so if we had more of those inch volume chunks of steel, well, and then it's kind of interesting. It's like you have to know something about leverage because, you know, make a problem simpler. Let's say I have out like a whole 2 feet and I have one of those 1-inch chunks of steel. And then I have it on a little teeter-totter, and then this is a rod, and or like a beam, massless beam. And then I come over here, and then let's say I just come out a quarter of a half a foot. So this is going to be 2 feet. You know what I mean? Where we have and we have a half there, a half there, a half there, and a half there. And then right here, hey, let's say now I just put a 1-inch chunk of steel. Well, obviously, you know, if this is our little teeter-totter, it's not going to be balanced at all. And then, yeah, so this kind of brings up, this kind of ties together the concept of statics, where it's just like you don't need to know anything about statics to know, you know, using integration to find the center of something. And, you know what I mean? And I guess, you know what I mean? Let's see. Yeah, but if you do know a bit about statics, it can make this finding the center of an area just way more kind of easy to visualize. If you're like, hey, that area has some oomph to it, you know what I mean? You treat that area, and even here, you wouldn't really necessarily have to treat this as a volume. You could just say you actually have a very thin, like, plate of steel where the thickness is just, you know, irrelevant, let's say. But each of these 1-inch chunks still have some mass to them. You know what I mean? They're not going to be 1/3 pound, but hey, they can still be substantial. And if you try to rest this on a very tiny table, you know what I mean? It is same principle. And I guess with centroidal, the centroid is when you have the equal amount of area on this side of this axis as you do on this side. And then if I have a perpendicular axis, and it really doesn't matter, I could draw any line, but if I have perpendicular, then the area over here is the same as the area over here. And you know what I mean, you should be able to see that I can draw any line at any sort of angle, and the area on both sides are going to be the same if that point is the centroid. Because no matter what axis I choose, hey, the weight over there is going to cause it to tip. But it's not just the amount, you know what I mean? The areas are the same. The amount of weight on one side of this axis is the same as the amount of weight on the other side of the axis. Is that even true? Alright, hell yeah. Hell yeah, that is true, but you come back to this, it's just like, well, why isn't this the centroid? You know, if I draw a line right here, there's the same amount of weight over there is the same amount of weight over there. So, sure, the centroid is a plane, or, you know, a point where if you draw an axis, yeah, you know, if you have a two-dimensional object and you're trying to find the center and you draw any line through it, you're going to have the equal amount of area there as over there. Alright, hell yeah. So we're going to find the area using double integrals. And I highly recommend watching this Houston Math Prep video on just that. So, booyah, we got into this. But then I had a question because when setting up the integrals, I was just like setting up the limits of integration. I don't know, it just didn't seem intuitive. So what we're going to do is that exact problem. I haven't even finished the video. So what I'm going to do is I'm just showing you kind of my learning process. Is like take a nugget and then try to go with it. And so in this video, what we're going to try to do is just, hey, try to do this like 4 different ways. Because in essence, we're going to do this. I saw this in my engineering mechanics book where you have the integral and then dA. And even in my book, they didn't even specify the region. You know, I didn't even kind of realize that if you have a little chunk of mass and then this is your region, then you integrate that little chunk over that region. And so this, and the only way to really do that mathematically rigorously to get an actual answer is using, you know, doing 2 integrals, one in one direction, one in the other. So that's what we're going to do. So we're going to say, hey, if we did have an axis here, xy, this thing is going to have a dx, dy. You know, this little area dA is going to have one side is going to be dx, dy. So then the area is just going to be dy dx, or more specifically, this small little area dA is going to be that. And then we're going to add up all those chunks. But the only way to really add them up is to, you know what I mean, add them up maybe this way first in a line, and then integrate top to bottom. Or do it this way first, and then integrate left to right. So that's kind of what we're going to do. We're just going to kind of go for it, you know what I mean? Because I want to be able to do this where, I don't know, like I just feel like I can't mess up because there's just 12 different ways to do it. So hopefully we come up with four different unique ways, or just even 2 different unique ways to do this. So there's our little area dA. I do know that if this is my x and y axes, that this is dx. It's a little change in the x. This is a little change in the y. Alright, so let's go for it. We're going to set up our double integrals. And this is going to be, might as well just start with the dx first. I have no idea. And then dy. But that's the whole point, is just like I don't want to flip out and just not be able to just kind of intuit my way through this. Alright, hell yeah. So, what do we want to do first? Like, you know, sometimes I try to do something and then it's like, nah, we're not doing it that way. So I guess we can just kind of throw in some other variables here. Hey, I could get out, so this is a dx, but it's a distance x away. Cool. And I could do the same thing here. And this is where I would want to draw like 4 pictures, or at least 2 different pictures. But we're going to see here, even right now, this is kind of the tricky part. So let's see if I can talk my way through it. Alright, so if I do have this little chunk dx, yeah, maybe, I mean, yeah, that was the thing. In the video, I think they were like, you know, like this is how I would do it. This is even if your equation gets kind of tricky. But I'm sure there's a way to do it like they do it in the video. I'm just going to say like, hey, I don't see it. I don't see it. So I'm just want to do it in like the way that I can just like, you know, just plow through and for sure do it. Alright, so here's our equation. So how I would do this is just, well, yeah, there's my dx and it's a distance x away. And sweet. So then I want to take this dx and I want to go from here to there. But, you know, this little thing's up there, so I got to go from here to there. Okay, so so that's going to be my limits of integration. And I think this is actually kind of one of the harder ways to do it. I think I chose the harder way. Had I chose to do it the opposite way, and we could do that. We could say, hey, maybe we ran into a roadblock, so let's back our way out. And then do that same process, but come over here. Let's talk my way through it. So I know that this is the little chunk dy, and then I know it's a distance y away. And I want to integrate that from y is equal to 0 to y is equal to, whoa, square root of x. Okay, hell yeah. So let's go back to the way you know, and we'll get there in a second, but you know what I mean? I think I'm okay with this, because I know that this is y is equal to the square root of x. I also know that this equation, you know, because this is y is equal to x to the 1/2. If I square both sides, you know, I mean, we can do that. Square both sides. That's going to be y squared is equal to x. Sweet. So this equation is going to be x is equal to y squared. So now I have my two equations for this line. And then so if I say that this is my little chunk dx and I want to integrate from, you know, here to there, but it's up there, so I got to integrate from like, hey, where it hits this line to over there. So, you know what I mean? So it looks like I'm going to integrate from y squared to, and then for this problem, they did set parameters. They wanted to go from 0 to 4. You know what I mean? And so if we integrate from x is 0 to 4, and yeah, they did a really good job, because I'm not math savvy even to write this. You know what I mean? I would have to watch a whole tutorial to be like, what are you doing? So x is 0 to 4, less than or equal. I see that. And then y is 0 to, well, yeah, they're saying if x is 0 to 4, y is 0 to the square root of x. Well, x is going to be 4, so yeah, so y is 0 to the square root of 4, which is 2. So y is 0 to 2. So hell yeah. So so we're just there on that. So I get that part. Okay, so sweet. So we have x is 0 to 4, y is 0 to 2. But for this integration, if I'm gonna use this little dx and I want to integrate from there to there, I have to integrate from y squared to 4. Cool. You know what I mean? And this is that whole process of like, well, that looked tricky, so let's do it simultaneously with the other way. So I'm going to have dy dx, and if I had it like this, and then that'll be fascinating to go back and watch this video to be like, like he showed a very simplistic way, but it was more of a trick. It seemed like a trick. It just didn't seem like from, you know, like plowing your way through. So that's what we're going to do, plow our way through. Alright, so I have this little dy, it's at a distance y, and so that can vary from 0 to, hey, x to the 1/2. So sweet. So I'm going to integrate this dy from 0 to the square root of x. Cool. Alright, and booyah. Alright, so let's do this one. How hard could it be? So we're going to and this is the integration here. We're gonna worry about this one later. You know what I mean? So yeah, even though this is y, so what are we doing? Well, I'm saying this is x is equal to y squared to x is equal to 4. So you know what I mean? My little dx right there, distance away from x, and it can be from, you know, x is y squared to 4. Yeah, that's x is equal to y squared. So that's what we have right there. And then this one over here, this is y is equal to 0. So I have my little dy, and we're going to integrate it from there. We're going to add up all those sums. And I guess that's the idea of integration, is you're just going to sum those little boxes, going to start there, and then go all the way up to, but I got to stop right there. And that's where my y value is the square root of x. Cool. And it's just, I get it. I get how this is, I don't think they did this in the video. Maybe they did, and I just didn't see it. But yeah, it's an arbitrary, you know what I mean? It doesn't paint the whole picture just because, you know what I mean? Like this is a variable. This upper limit's a variable, but then we take it from there to there. And then, well, we have another upper limit as a variable. But I don't know if there's more. I'm sure there's multiple ways to do this. I'm just choosing two. And I don't even know. It's probably the same thing that this video maker. But yeah, it's really good. I learned a lot, even from, did we talk about regions? I think we did. Alright, booyah. Alright, so slow roll, and here we go. So we're going to integrate this dx. So that's just going to integrate to x. So I still have this integration. We don't know what the limits are yet, but heck yeah. So I'm going to integrate this dx. We're going to get x. And then we have the limits of integration from 4 and starting at y squared to 4 and dy. So now we can evaluate this. So we still have this limit. We don't know what those are yet. You know what I mean? Who cares? Just one step at a time. And then we have this is going to be 4 minus y squared. Alright, hell yeah. So now we're getting places. So now we have... so now what did we just do? We just added up all these boxes, so we found this area. Cool. So now we're back to a slice, and I think this is No, maybe I did mess up. Yep. Because you know, now we would have to have a dy, and we don't have a dy no more. We just have a big old area, and I can't integrate on dx again. So, oh yeah. Okay, yeah, I throw in the towel. I apologize for even making this video. But it's just interesting because I think it is useful to be like, oh, I don't see what you did there. And, like, why can't I just do it this way? Start to plow through and then get to the point where you're just like, oop, nope, I can't integrate that no more. You know what I mean? Because I have this dy and, yeah. That is a bummer. Alright, I gotta take a pause on this one. Alright, hell yeah. I don't know if this what makes my videos juicy or not, but we made a mistake. Like, obviously that is not the area that we even did. And that also goes again, you know, I mean, the whole idea of plowing our way through is to, you know, talk our way through it verbally. So sure, we had this dx little chunk. That's just this little width. And then we were going to add them from this little side to this little side. I have no idea where I started going vertical. So this little integration was, sure, it was taking this little dx width, but then we're going to integrate it from an x value of y squared to 4. And so if we add up all of these little squares, you know what I mean? I should do little squares. Hell yeah, this is the area that we're going to get. So my bad, I apologize. But hell yeah. So so this integral was this area. And now, what does this say? This says that we have a dy slice, and then we're going to integrate. So we're going to take this little slice, and then we're going to add up, you know, the slice right here and the slice right there. We're going to have a slice at the bottom, a slice at the top. And then so those slices are going to be from a y value. So we have a dy, and we have a y value of 0 to a y value. So the highest y value up here is going to be y is equal to square root of x. So we have 0 to the square root of x. Alright, hell yeah. And maybe we'll do it this way right at the end. Alright, so sweet. So let's integrate this. We have a dy we're going to integrate. So just, I guess at this point, you know what I mean? I guess I just trust the rules of integration. But I shouldn't. I mean, this is where I should be spending another hour or two studying, being like, hey, do you even mentally know why? Like, if you add these slices up, well, and I think it's doubly hard because, hey, this is now just like a function, 4 minus y squared, which is, yeah, that's kind of fascinating. That's the area of this chunk, but it's just the area of this little slice is represented as this function. And then you're going to have the limits up against kind of another function. Oh, and I guess here is Oh yeah, this is interesting because this makes it open-ended. We should just put 2 there because our x value is 4, and we're going to go from 0 to 2. So, oh yeah, why didn't I just see that? You know, why didn't I just see that we're going to integrate this slice from 0 to 2? I just thought we were going to go from 0 to the top of that graph. And so why couldn't I have done that over here? Well, we were going to integrate this little slice from, we had to start over here. We couldn't just start at 0. We had to start at that equation and go to, we could go to 4. But yep. But now, because we set our x bounds from 0 to 4, you know what I mean? Yep. Anyway, all right. So let's integrate this, and we're gonna have 4 integrates to 4y minus, this is a y squared, so we're gonna have a 1/3 y squared, and then we're going to evaluate from 2 to 0, and so we're gonna have 4 times 2 minus 1/3 2 squared. That's going to be 4. It's going to be 4/3. So we're going to have 4/3. We're going to have 8 minus 4/3. That's going to be 24 minus 4. It's going to be 20/3. Alright, hell yeah. So is that the area? And I better just use some numerical methods. And so we're going to go square root of x. We're going to graph that puppy. Alright, and we're going to integrate from 0 to 4. And we get a value, yeah, of 5 1/3. Is that what we have here? You know what I mean? 5 times 3? I don't think so. 5 times 3, that would be, or 5, if I have 5 times 3, that would be 15. That would be 15/3. Wait, is that right? I'm doing something horribly wrong. How many thirds is this? Oh, yeah, never mind. No, this would be like 6 2/3. So now we got the wrong answer, but that's all right. All right, back to the drawing board. But let's try to do it this way. So I'm going to take this dy slice, and then I'm going to integrate it along the y from 0 to x squared. Sweet. So that's going to give me, when we integrate this, I'm going to get a y, and then those are my limits, and then so I'm just going to have x squared dx. And then when we integrate from x, I'm going to go from 0 to 4. So 0 to 4. And, no, I see, yeah, I see the issue there. Oh, no, that is, no, duh, because if this was the equation, obviously, the integration of this area would just be vertical slices from there to 4. And that's what we have, you know, so this would be x to the 1/2, we would have x to the 3/2. Oh, did I mess up somewhere? Hell yeah, I messed up somewhere. Why did I... Oh, never mind. Yeah, I gotta watch the rest of that video. Alright, so this would be x to the 1/2. When we integrate, we get x to the 1/2 plus 1 divided by 1/2 plus 1. That's going to be x to the 3/2 divided by 3/2, which is 2/3. So we're going to have 2/3 x to the 3/2 evaluated at 0 to 4. Yeah, 0 to 4. So we're going to have 4. We need to square root it and then cube it. So that's going to be 2 cubed. That's going to be 8. 8 times 2 is 16. 16/3. So we got 16 divided by 3. And hell yeah. So we get the right answer there. I don't know why we messed up here. Let's double check. But I don't know, you know what I mean? This is where the struggle is real. It's like when you kind of know something just barely. So let's crank through that one more time. I want to integrate this little dx, this little slice, and I want to do it along the x values from x is equal to y squared to x is equal to 4. Okay, sweet. And so that's going to give me 4 minus y squared. And then and we're going to have that other integral. So we're going to have integrate 4 minus y squared from, you know, dx now. So I'm going to have, no, see, no, we're going to have dy. So sorry about that. So we're going to have dy, and we're going to go from here to there. So my y value is, well, it's just 0 to 2. Yeah, so this should have worked. I don't know why it didn't. When we integrate, we're going to get 4y minus y to the 2 plus 1 divided by 2 plus 1. So that's going to be 4y minus 1/3 y cubed. Evaluated 0 to 2. Oh, so here, yeah, I might have messed up on the cubed. No, did we get 8? Yeah, so we get, oh, it might have messed up right there. So 4 times 2 is 8. Yep. And then, oh, and I just did squared right there. My bad. So there you go. There's the error. So we have 1/3 2 cubed minus 4 squared. So we have 8 minus, this becomes 2 cubed. So that's 8 thirds. Sweet. So we have 24 thirds minus 8 thirds. And that's going to be that 16 thirds. That's going to be 5, because 15 thirds is 5. So we have 5 1/3. Alright, hell yeah. That was brutal. And so now I'm just very curious to see if there's a rhyme and the reason for doing it kind of like in a, I don't know, I think this person does it in a different way. But man, that was a struggle. But I don't know, do you like videos where you actually get to see the errors being made and then just having them faster? So now, I guess what I'm going to do right now is what I should be doing at the end of every video. You know, and this is where people actually do this. Like, no one does videos like this, because why would you want to show your mistakes? Like, all we did was just make a mistake on a cube. We just said this was squared instead of cubed. It's a very simple mistake. A mistakes on exponents, a mistake on negatives, you know, those are the most common. So this was cool because we did it 2 different ways, and so we were able to get our answers to match. Okay, so now what I'm going to do, I'm going to be done with this video, but I'm going to go back through and see just how simply I can do it. You know, because I definitely need to work on that. Alright, so, hell yeah.